Over the past 24 hours, the Sun has entered a particularly active phase, producing **10 solar flares in a single day. While solar flares are powerful bursts of radiation from the Sun's surface, the bigger concern for Earth is that several of these eruptions also launched coronal mass ejections, CMEs, massive clouds of magnetized plasma traveling through space. Multiple CMEs are now on a path toward Earth, and forecasters expect they could arrive around the beginning of the July 4 holiday weekend. A CME is very different from a solar flare. A solar flare is essentially a flash of intense electromagnetic radiation that reaches Earth in about 8 minutes. It can briefly disrupt radio communications on the sunlit side of Earth, but usually has little lasting impact. A CME, however, is a giant cloud containing billions of tons of charged particles and magnetic fields. These clouds travel much more slowly than light, typically taking 1 to 3 days to reach Earth. When they collide with Earth's magnetic field, they can trigger geomagnetic storms. The recent activity originated from several magnetically complex active regions on the Sun. These regions contain tangled magnetic fields that can suddenly snap and reconnect, releasing enormous amounts of energy. That process produces solar flares and often hurls CMEs into space. Because several eruptions occurred within a relatively short period, scientists believe that multiple CMEs could arrive one after another, or even merge together during their journey. If that happens, the combined impact can sometimes produce stronger geomagnetic disturbances than a single CME alone. Forecasts currently indicate that Earth could experience G1 minor to G2 moderate geomagnetic storm conditions. On the 5-level geomagnetic storm scale used by the National Oceanic and Atmospheric Administration, G1 storms are the weakest, while G5 storms are considered extreme. A G1 storm can produce minor fluctuations in the power grid, slight impacts on satellite operations, and auroras visible slightly farther south than usual. A G2 storm is more significant, potentially causing increased spacecraft charging, temporary interruptions to high-frequency radio communications, and stronger auroral displays reaching much farther from the poles. The biggest excitement for many people is the possibility of seeing the northern lights, also known as the aurora borealis. Normally, the aurora is confined to high-latitude regions such as Alaska, northern Canada, Iceland, Scandinavia, and parts of northern Europe. During a G1 or G2 geomagnetic storm, however, the auroral oval expands southward. Residents in northern U.S. states, including parts of Washington, Montana, North Dakota, Minnesota, Wisconsin, Michigan, Maine, and northern New York, could have a good chance of seeing the lights if skies remain clear. If the storm briefly becomes stronger than forecast, auroras could potentially become visible even farther south in states such as South Dakota, Iowa, Nebraska, Illinois, Indiana, Ohio, Pennsylvania, or Oregon, although that is less certain and depends on the exact strength and orientation of the incoming magnetic field. The timing of these displays is especially notable because they coincide with the July 4 holiday weekend. Many people will already be outdoors during the evening watching fireworks or attending celebrations, creating an unusual opportunity to look toward the north horizon after dark. The best viewing conditions occur away from city lights, under clear skies, between roughly 10 p.m. and 2 a.m. local time. Even if the aurora is faint to the naked eye, smartphone cameras often capture colors that are difficult for human eyes to detect. Scientists will be paying close attention to one key factor as the CMEs approach Earth: the direction of their embedded magnetic field. If the CME's magnetic field points southward, opposite Earth's northward magnetic field, the two fields connect more efficiently, allowing energy to pour into Earth's magnetosphere. This process intensifies geomagnetic storms and leads to brighter, more widespread auroras. If the magnetic field points northward instead, much of the CME's energy is deflected, resulting in weaker effects even if the CME itself is large. Most people on Earth will notice little more than enhanced auroras, but space weather can affect modern technology. Satellites orbiting Earth may experience increased drag from the expansion of the upper atmosphere, forcing operators to make small orbital adjustments. GPS accuracy can temporarily decrease. High-frequency radio signals used by aviation and maritime operators can become unreliable, and electric utilities monitor power grids for induced currents caused by geomagnetic disturbances. Modern infrastructure is generally well prepared for G1 and G2 storms, and widespread disruptions are not expected. This burst of solar activity is occurring because the Sun is near the peak of its approximately 11-year solar cycle a period known as solar maximum. During solar maximum, sunspots become more numerous, magnetic fields grow increasingly complex, and solar flares and CMEs occur much more frequently. Over the past year, solar activity has repeatedly produced impressive impressive aurora displays across much of North America and Europe, and scientists expect elevated activity to continue for many months. As the incoming CMEs reach Earth, space weather forecasters will monitor data from spacecraft positioned between the Sun and Earth. These satellites provide about 30 to 60 minutes of advance warning before the solar wind actually strikes Earth's magnetic field. Once the CMEs arrive, forecasters can quickly determine whether the storm will remain at G1 levels or strengthen toward G2 or higher. Overall, current forecasts suggest that the July 4 weekend could feature minor to moderate geomagnetic storms, creating a good opportunity for northern lights viewing across much of the northern United States and southern Canada, while only minor impacts to satellites, radio communications, and power systems are expected. The exact intensity of the auroras will depend on how the multiple Earth-directed CMEs interact with one another during their journey, and how their magnetic fields align when they finally reach Earth's protective magnetic shield.